Hello, in this video I'm going to talk about a technique of integration which is not very well known, or at least I didn't know about it up to 1 year ago. And But before directly going to the technique of integration, let us tell you a little bit of history about that. I remember when I was a teenager, when I was in my high school studies, I got to know about integration theory, of course, the standard ones at the level of calculus. And I was so fascinated by this topic that I soon started actually mastering all well-known standard techniques of integration at the level of calculus, for example, Thomas calculus at that time. And then I was always trying to find challenging problems. And then I remember my math teacher gave me a problem that I remember clearly. It was integral to calculate this definite integral from 0 to pi over 2 of this function sine x divided by sine x plus cosine x dx. I was supposed to calculate this integral I. Yes? And of course, as a novice student, when you study calculus and you want to calculate definite integrals, the first thing comes to mind is fundamental theorem of calculus. Okay, uh, you just try to calculate a primitive function for your integrand, and then using the fundamental theorem of calculus, calculate that primitive function at these two limits, and then subtract them. That will be your answer. So for a novice student in calculus, usually integrals, these definite integrals, is not a big problem. The only problem you think about is how to find the primitive function for this. And I was not an exception. I tried to find a primitive function for this function, and then I would say that that is just a minority to plug these numbers there into primitive function and find the answer. And because, as I told you, I already mastered all standard tricks in integration, I didn't find this problem hard. Yes, I know it was lengthy, but technically speaking, I was sure at that time that I could find a primitive function for that, because one of the standard techniques of integration is talking about integrals of the form r sine x cosine x dx, in which r is a rational function in two variables. Okay, and then you see that this function is a function of sine x and cosine x. And I knew that if I have an integrand like this, in principle, I can introduce a substitution variable, but of course I have to use this trigonometric identities, that sine x can be written as 2 tan x over 2 divided by 1 plus tan x over 2 to the power of 2. And we have a similar formula for cosine, which is 1 minus tan x over 2 squared divided by 1 plus tan x over 2 squared. Okay, and then you introduce the variable to u to be tan x over 2. Then from here you can immediately understand that x over 2 is tan inverse of u, and then you multiply by 2 and differentiate because you need to have your dx. So x becomes 2 tan inverse of u, and then dx becomes 2 du 1 over u squared. This is the standard derivative of the tangent inverse function. And then you can, let me continue here. So then you can write that integral of sine x over sine x plus cosine x dx can be written in this form. Integral, instead of sine x, I put 2 times u divided by 1 plus u squared. And in the denominator, instead of sine x, I use the same expression. And for cosine x, I would write 1 minus u squared divided by 1 plus u squared. And then instead of dx, I put this expression. Okay, and then for example this becomes equal to the integral if I multiply the numerator and denominator by this factor. So the numerator becomes 2u multiplied by that u, that 2 becomes 4du, and the denominator becomes 2u plus 1 minus u squared. And of course this factor will also go to the denominator, and then you get this expression. And for example, I can factor a minus 1 out and a 4 out from here. This becomes integral of du. Oh, sorry, I forgot to put this u there, so there's also a u here. And then it becomes u squared plus 1. I factor a minus sign out, so it becomes u squared minus 2u minus 1. Yes. And this was already known to me that I can solve this integral because this is a very standard integral. It is tedious, I agree, but in principle doable. I use the method of partial fractions, decompose this rational expression to the sum of two fractions, and then I continue. But of course you know that before doing that, because the discriminant of this quadratic polynomial is positive, so this can be factorized to a product of two first degree polynomials, so I have to do that. So in principle I have to decompose this fraction into the sum of three fractions, and each one of those fractions will be a function so that I can easily calculate its integral. It gives me an integral in terms of u. Then in that function I have to replace u with this expression and then calculate these things. I'm sure that I was able to do it by really spending so much hours at that time to solve this problem. But then I was very happy. I wanted to show that my teacher the solution. Then I was shocked with his way of solving the problem. At that time, I didn't know about this very famous theorem. He actually used this theorem and showed me that how can I solve this problem much simpler. So he told me that if a function f is somehow, I'm just talking in a little bit more advanced language now, I didn't know about these things back then. So if a function is integrable on a closed interval from a to b, then integral from a to b f of x is dx is equal to integral from a to b f of a plus b minus x dx. By the way, I can immediately prove this for you heuristically. This is not a very big problem. For example, if I want to start from here, I can call a plus b minus x capital X. Then I would say that my little x goes from a to b. So if little x is a, capital X becomes b. Yes, x goes from a to b. This implies that the capital X, if I put a here, b is left. Then if little x is b, capital X becomes a. And then from here, if I differentiate both sides, this becomes minus dx, and the right hand side becomes d capital X. So this integral that you see here, integral from a to b f of a plus b minus x dx, is equal to integral, instead of from a to b, I go from b to a, and this becomes f. Instead of this expression, I just put capital X, and instead of dx, I put minus d capital X, and I use this minus to swap these two limits. So this becomes equal to the integral from a to b f of capital X d of capital X. And of course, you know that the variable of definite integration is a dummy variable. What does it mean? It means that if I rename all the variables of integration to some other letter, the value of the integral remains the same, yes? So this means that I started from the right-hand side of this, and I was able to reach to the right-hand side with the difference that now instead of little x, I have capital X, but as I explained, it doesn't matter because the variable of definite integration is a dummy variable. So this is not a very hard one. Of course, if you want to do it rigorously, that is also possible, but that is the essence of proving this one. How this problem will help me to solve my original problem. So that is the case. So if in my integral, so let me bring my stick. So in my integral, this is my function f of x, little a is 0, little b is pi over 2, okay? So f of x is sine x over sine x plus cosine x, yes? And then a is 0, b is pi over 2. If I calculate f of a plus b minus x, this becomes f. A is 0, b is pi over 2, so this becomes pi over 2 minus x. But f of pi over 2 minus x, it means that I replace every x with pi over 2 minus x. So this becomes sine of pi over 2 minus x over sine of pi over 2 minus x plus cosine pi over 2 minus x. But you know that sine of pi over 2 minus x is nothing except cosine x. So this is also cosine x. But cosine of pi over 2 minus x is simply sine x. Okay? So then what does it mean? This means that if my integral, which I called it I, is equal to integral from 0 to pi over 2 sine x over sine x plus cosine x dx, if this integral is I, this integral is the same I. So this means that I can also be viewed as integral from 0 to pi over 2, but this function dx. But this function is this. Dx. So far, I haven't calculated this integral at all. What I have done, I have used this theorem to guarantee that if this integral, if my original integral is I, this integral is also I. But what is the benefit of knowing that these two are equal? The benefit is that now I can add them side by side. So the left-hand side becomes I plus I. The right-hand side becomes integral from 0 to pi over 2 sine x over sine x plus cosine x dx. And then plus integral from 0 to pi over 2 cosine x over, if you don't mind, let me write it, sine x plus cosine x dx. But we know that if I have two integrals with the same interval of integration and I want to add those integrals, I can write one integral and add the integrands. So then it becomes sine x over sine x plus cosine x, and then plus cosine x over sine x plus cosine x. And now hopefully you see why this method is superior to what I naively did when I was at my high school studies. Why? Because if I add up these two fractions, the denominators are the same, the numerators will be added, but when I add the numerators, it becomes exactly the denominator. Yes? But this fraction is just 1, so this becomes integral from 0 to pi over 2 1 dx, and this is the simplest possible integral ever. Yes? So this becomes x. I have to run it from 0 to pi over 2, which becomes pi over 2. But be careful, this is not my I. This is I plus I, which is 2I. So this means that 2I is equal to pi over 2, and I finally I'm able to calculate this. This is the method that my teacher told me at that time, and I was really fascinated by this one. The lesson was that, okay, sometimes, so fundamental theorem of calculus is not the only way to calculate definite integrals. Might be there are some outside of box thinking involved in the problem. This was one of them. I was really enjoying the solution of the problem. And then when I myself became a teacher, I was always using this example to show my students that, okay, when it comes to definite integrals, of course, the one standard way to tackle any definite integrals is fundamental theorem of calculus and finding the primitive function for the integrand and use the fundamental theorem of calculus, but that is by no means the only way. And for a long time, I was thinking that, okay, this problem is actually designed to teach us this lesson, that fundamental theory of calculus, even though very important, is not the whole story. Okay, and I was thinking that, okay, my calculation was also possible, but it is tedious. But I hope that you see that if I change this integrand to a more complicated one, let us say that they ask you to calculate this. So let us say sine 5x divided by sine x to the power of 5 plus cosine x to the power of 5 dx. Then, in principle, it might be possible to use this method, but then you see that it becomes horrible, yes, because then I have to raise them to power 5. But I hope that you can immediately see that the answer to this integral is exactly pi over 4 again, because I can use the same trick. If I use the same trick, then f of pi over 2 minus x will change sine to cosine and cosine to sine, and when I add them up, the numerators and denominators became the same, and then integral becomes pi over 2, and then I have to divide by 2, it becomes pi over 4. So at least you can feel that this method is completely superior to that naive method, okay? So you can solve these problems, okay? There are many types of these problems you can investigate. If I can, for example, remember, so you can calculate this integral using this trick. I will leave this as an exercise. For example, let us say that I have x to the power 100, and then I have x to the power of 100 plus 1 minus x to the power of 100 dx. Okay, so call it I, and then use this trick that I just told you, and then calculate this integral. The integral should be 1/2, I think. So if you calculate it correctly, the answer will be 1/2. Okay, but still, I haven't even started the method that I want to teach. So that was just a little bit of history if you're interested about stories, okay? But now, nearly 1 year or 1 year and a half ago, I got to know a book. Okay, so let me show you the book. So this is the book, Classical Analysis and Approach Through Problems by Hong-Wei, if I can pronounce it correctly, or Hong-Wei Chen. Okay? And then I saw that he has introduced a very nice method for calculating this integral. Okay, so integral sine x over sine x plus cosine x dx. Be careful, not the definite one, the indefinite one. Okay, and it caught my eyes, it caught my attention because I remembered that nice problem. And the way I was thinking that, okay, if I look at the solution, he will solve the problem as I did as a high school student, and I will feel proud of myself. Okay, but then I was really shocked to see the way he solved the problem, or she, I'm not sure. Okay, so let us call this Chen's method, okay? Because I don't know how many of you have seen Feynman's trick, so we can call this Chen's trick, because this is the first time I saw it in this book. Okay, and I haven't seen, to be honest, in any other books, because I'm very interested in calculating integrals, and I will try to learn a lot about these integrals when I am bored, I usually sit down and try to find a very nice integral and solve them. Okay, but I haven't ever seen this until 1 year or 1.5 years ago. So he calls this integral I, and he introduces another integral j with this. So be careful, this problem is an indefinite integral from the beginning. So this is, we just want to find a primitive function for this one. Okay, but why this will be helpful if I introduce this integral? Okay. The first observation is probably motivated by that trick. So it is probably not hard for you to understand that now we can add them up. Okay? Because if I add them up, first, be careful. I don't know this answer. I don't know this one. Okay? So I'm actually making my problem even harder. I don't know this integral. I bring another integral which I don't know. Okay? But now, if I add I plus j, what happens? For the same reason, these two integrals will be combined, and this fraction will be added to this fraction, and now the numerator becomes exactly as the denominator, so it becomes 1 dx. And if I calculate this, this is just simply x. Of course, if you want, you can put a constant of integration here. But the interesting thing is this one. If you subtract these integrals, what happens? So let me see which one is suitable. Let me subtract j. Let me calculate j minus I. Okay, so that was the nice trick. If I calculate j minus I, what will happen? I have to subtract the integrands. I can combine two integrals into one integral on the condition that I combine the integrands. So it becomes cosine x minus sine x over sine x plus cosine x. Okay, can you see what is going on now? Because this new integral can also be calculated very easily, yes, by substitution method. If I take the denominator u, I hope that you agree, the derivative of sine is cosine, the derivative of cosine is minus sine, so this is just du. So if I take this u, this is just the u, so the answer becomes ln of absolute value of c plus a constant of integration, let me call it c prime, for example. And then I replace u with this expression. So this becomes ln of absolute value of sine x plus cosine x plus c prime. So what do I have? I don't know I don't know j, but I know what is I plus j, I know what is j minus I. So I solve a system of equations in terms of I and j and find I and j. So as a bonus, I not only get the answer to this integral, as a byproduct or a bonus, I will also get an answer to this integral. Okay, let us do that. So for example, because my goal is to calculate I, so if you don't mind, let me multiply this by minus sign and add them side by side. Okay, so let me write this I plus j. And if you don't mind, let us get rid of the constants of integration. I will add one overall constant at the end of the problem. So I plus j becomes equal to x. Here, if I multiply this by minus sign, I minus j becomes a negative of that, minus ln of absolute value of sine x plus cosine x. Okay? And then I add them side by side. So what happens? This j is cancelled. I plus I becomes 2i. And this becomes x minus ln of absolute value of sine x plus cosine x. Yes? Yeah, I'm recording. Yes. So x minus ln of absolute value sine x plus cosine x. Then I divide everything by 2 because I'm looking for I. Now, if you want, in principle, we are supposed to add a constant of integration. Let me call it again c. So that is the answer. Wasn't it beautiful? To be honest, I'm not sure because I don't remember my integrand. If my integrand was exactly the way that I did it using partial fractions, I don't remember if it gave rise to this answer, but now this is your integrand. As a bonus, let us calculate this integral that I started from the beginning, yes? Sine x using this now. Cosine x dx. So this becomes this, calculated from 0 to 1/2. Yes, if we have done everything right, the answer definitely should be pi over 4. Is it? Definitely yes. Because if I replace x with pi over 2, this becomes pi over 4. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. ln of 1 is 0. So this doesn't play any role. Minus, if I replace x with 0, this becomes 0. If I replace x with 0, this becomes 0. This becomes 1, but again, ln is 0. So yes, what we did was indeed correct. That's a confirmation. So if I ask you what j is, now that you have I, you can put it here, move it to the other side, and then you find your j. So this is a nice trick that he used to solve this integral. Okay? So I want you to know this about this trick. I think it was really a beautiful one. For example, as a bonus problem, I can ask you to do this. You hopefully know how to do it yourself. I mean, so integral e to the power of x divided by e to power x plus e to power minus x dx. Okay, of course, this you can calculate it just by method of substitution, just tackling to the problem itself. It will not be that hard, but I want you to guess what is a good choice for j so that this trick will again work. Okay, now the reason that I remembered this book that I saw 1 year ago is because when I published the video was this. The video was about this problem. In that problem, we had this equation, integral from 0 to x, t squared over 1 plus t to the power of 4 dt equals to 2x minus 1, if I remember correctly, something like that. And we were supposed to see how many solutions for x this equation has on this interval. Okay, and of course I didn't calculate this integral. If you watch the video, then you will see that I use intermediate value theorem and this fundamental theorem of calculus for differentiating an integral, okay, and things like that. But I didn't even started calculating this integral, okay. And then one of the viewers actually asked the question, and that is why I remembered I saw this in this book that I introduced. So the credit is his, okay? But I will make a video for you. But by then that the video is ready, you can think about it yourself. This is much more tricky than the examples that I provided here for you. So in this book, he solves this integral, yes, using this trick. Okay, so let us call this I. My goal is to calculate I, and I can also give you the hint, because even might be the hint is there, it is not as straightforward as these problems that I introduce here. So the hint is to consider j to be this integral. Okay, yeah, I recommend you to sit down and think about, can you use this method? Because again, I was able to solve this using a standard method. By the way, this is not a hard problem because it's a rational function, okay? And then you factorize the denominator and then use the standard method of partial fractions. So in the video that I am preparing for this, I will solve this using the standard method. It is tedious, but not impossible. I mean, probably in 15-20 minutes you can solve this integral from scratch by standard methods. But in this book, he has offered another method, which is again fascinating. The idea is the same idea that I introduced here for you, but look how you can use this and that with the same kind of idea to solve both of them. So always as a bonus, you get the answer to another integral. Okay, so I hope that this video was useful for you. In this video, I used the landscape mode. Please let me know in the comments which one you prefer, because usually making videos in landscape mode is much simpler, technically speaking, yes, than the vertical mode. But if you don't like it in that way, please leave a comment so that I know which one you prefer. Anyway, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.